It's my pleasure to introduce Mario Sanchez as our first speaker of the day, and he will be talking about, he's local here, and he will be talking about direct categories of Permutahedral varieties.
Okay, for the introduction. Yeah, today I'll be telling you a little bit about the sort of variety associated to the beloved permutahedron. Now, if you've been here, you know that previously I gave the same talk. I don't know what I was doing with my hands, but I gave the same talk, a very similar 20-minute version of this talk at the postdoc talks. And for that talk, the story I chose was a pretty standard one. Namely, it went something like this. There are these things called Derived categories, which certain people care about, growth they cared about, like the people whose homological media symmetry care about. And there is some combinatorial way to approach that and calculate explicit descriptions of that category. And that was kind of the talk I gave. And if you're interested in that, you can go take a look at that. However, placing the motivation as me being interested in derived categories is just not really true. Really, I came across this project in a completely different way. And this is somehow the unique audience that can sort of appreciate, or hopefully appreciate, why I came at the derived category the way I did. And so I'm going to take a different motivation for this object, closer to the truth. And because it's closer to the truth, it's a little not as direct and a little bit wishful thinking, but you'll see as we go along. So I'm going to begin seemingly far away with something called the theory of valuations of polytopes. So this is something a lot of people in the audience have mentioned a couple of times throughout the talks. So for me, given a collection of polytopes in the same ambient space, we can study the space of indicator functions of these polytopes. So I have these indicator functions here, which are just functions that are one if x is the polytope and 0 otherwise. I'm going to take z linear combinations. This is a Abelian group one could define. Then we can study the notion of a strong valuation. This is a function that goes from the formal linear combinations of polytopes in your family to some Abelian group, typically like polynomials or something, such that map factors through the space of indicator functions, corresponding to the natural map that sends a polytope to its indicator function. So practically what this means is that if we think about the space of indicator functions, we have some relations appearing in this Abelian group. And this is probably a picture that a lot of you in the audience have drawn at some point. We have, for instance, if we take all polytopes, we have that this octahedron can be written as the top square pyramid plus the bottom square pyramid minus that square in the middle as indicator functions, right? And so for a function f to be a valuation, we require that it must also satisfy the corresponding equation if we plug in these polytopes into f. And it must do so for every relation coming from the space of indicator functions. Something to mention here is that depending on your family P, it's not necessarily true that we're getting only families from subdivisions, right? You might have more interesting linear combinations. Although in some situations, these are actually the same. Now, this is sort of a subject in convex geometry. And so there's a collection of natural examples that come from convex geometry. For instance, if we take a family of lattice polytopes, we have things like the Urha polynomial, things like volume functions, things like just a constant function, which is 1 on every polytope, and more things like intrinsic volumes, formulas involving angles. And so these are somehow natural examples that arise convex geometry. But for me, the more interesting class of examples happen when we choose P to be a special class of polytopes, namely, well, major polytopes, which seminars, this workshop is about. So if you take P to be the class of major polytopes on a given ground set, then you can ask the seemingly nonsensical question, take your favorite invariant of matroids, view it as a function on polytopes, is that valuative? And the first results that really started serious study of this is a very surprising result by David Spire, a paper on tropical linear spaces, where he shows that the assignment of the major polytope to the top polynomial is a valuation. It was in a slightly different language than what I'm using, but it's equivalent. And as a consequence, of course, this means that any growth-unique invariant, things like characteristic polynomials, beta invariants, and so on, are all also examples of valuations. Again, I claim that this is weird. Right? We took a purely combinatorially defined invariant, viewed it as polytopes, and it turned out to be a valuation. Right? Since then, there's been many examples of valuations of matrices. And I have a bunch of examples, and I wish I could write even more. I know that there's a lot of examples of people in the audience, and I just can't fit 20 examples. But I wrote some examples trying to get different people in the field. For instance, you get things like Chris here studying the volume polynomial of a matroid, which is encoding the Chow ring, that he proved its evaluation. Dirksen defined an invariance, which later with Fink proved there was evaluation and it's universal in some sense. You get some statements from geometry, like in the BEST paper, they prove that various different K classes of the nice bundles are valuations. In fact, they use this kind of as a way to help define these for general matrices. Okay.
There's a question.
Yes.
Sorry, I'm going slow. Could you just clarify the definition of the valuation, but only for matroid polytopes?
Yeah.
Like,
so what this means, actually, this picture here is a good example. This picture is actually a relation within the world of matroid polytopes. It's my uniform matroid, and I'm decomposing it into some matrices. This means that if you calculate the topolonomial of this, it will be the topolonomial of this plus the topolonomial of that minus the topolonomial of this. And the same is true for any of these other invariants that I wrote. So for instance, Lucia, Felipe's, and Chris's CSM classes of matroids is an example of a valuation. And so if you calculate those values, it will satisfy the relation. And actually, it's kind of hard to find a naturally occurring matroid invariant, which is not a valuation. I mean, there's lots of examples. It's easy to cook up non-examples. So there's lots of reasons to care about this. And one is it helps you define things from realizable to non-realizable. Others, like Rees and Benjamin will show, or have shown us, they're a powerful tool for disproving conjectures by studying valuations on special classes of polytopes. And in general, it seems to be some sort of general property that we want to understand.
Excuse me. So I understand that if a number or a polynomial is evaluated, but what does it mean by CSM classes evaluated?
Yeah, so in the notion of valuation that I have, it's important that things are taking values in an abelian group.
Yes.
And so you have to choose the correct abelian group. And so here, maybe you're looking at the Chow ring in a tropical way, thinking about Minkowski weights on the fan of the braid arrangement. And so each of these things has its own place where it's being defined. So for these, for instance, you probably want to be defining them in the K ring.
The CSM class usually lives in the Chow ring.
Yeah.
And you're saying the Chow ring sits in a bigger.
I'm taking my Chow ring as the abelian group, just the underlying abelian group, the Chow ring. Of the other, sorry, yes, of the Permutahedron, yes. Minkowski weights on the braid fan.
Okay.
Yeah, thank you.
Sure.
Okay, so one of the interesting results, which is closely related to this Dirksen-Fink invariant, is that we actually know a nice basis for this space of indicator functions on a class of matroid polytopes of a given ground set. And what Dirksen-Fink proved is that there's a basis given by a class of matroids, which have actually appeared many times through very different names, like generalized Caroline matroids, shifted matroids, and so on. And for me, I'm going to use the word Schubert matroid. And as usually defined, Schubert matroids can be described as lattice path matroids, where you take the bottom path in the grid, and you're considering the paths in between, labeled in a certain way. But for this, it's important that we're considering Schubert matroids up to isomorphism. So typically here, there's a preferred linear order in the ground set, but I'm choosing them with respect to everything. And these are related to the Schubert decomposition of the Grassmannian, which is where this particular name comes from. Okay. This has an implication, which is that valuations on matroid polytopes are therefore determined by the values on Schubert matrix. If you know those values, then this determines the valuation on all matrices. And so this leads to some dreams that are kind of ill-founded, which is, oh, maybe I'll understand my valuations on Schubert's and then understand everything. But the problem is that the expansion of matrices into Schubert's is not necessarily an easy thing. But you can use this to construct sort of called universal valuations by viewing kind of dual functions on this basis or related basis.
So what was the arrow here? What was implying this?
The statement that there's a basis given by Schubert matrix.
Right.
So said differently, the indicator function of any matroid can be written as a linear combination of indicator functions of Schubert matrix. In the original example I showed, the octahedron, the two square pyramids, and the square, that square is not a Schubert matrix, but the other three things are. And so you can rearrange to express the square in terms of those three objects.
What's LPM?
LPM is lattice path matrix.
Do you plan to explain to us what's the Schubert matrix?
Not really. I don't think it'll be too important for us. Yeah, so the two matrices are matrices that are isomorphic to this lattice path matrix. From a geometric perspective, these are moment map images of Schubert varieties in the Riemannian. Okay. So one of the things about these examples is that a lot of these examples are, in some sense or another, some sort of shadow, a combinatorial shadow of some other algebraic or geometric invariant. Right? For instance, you might know that the volume polynomial, as I mentioned, is encoding the Chow-ring of a matrix. The convolutive polynomial is closely related to intersection homology of matrices, and so on. A lot of these things have some sort of geometric or algebraic object behind it. And so a natural question, a natural problem, is to try to find some way to contain more information than just the numerical shadow. In other words, try to categorify the theory of valuations. And there's two possible ways you can go about this, at least. The first way is you can try to find a categorification of the space of indicator functions, and then try to define valuations as things that factor through this in some natural way. The second way is a slightly more direct approach, which is to study special assignments, where you assign an algebraic object, like maybe let's just say graded vector space or something, to every polytope in your family, to each matroid, and to inclusions of polytopes, you assign some sort of morphism. This is some functor from some category built on your polytopes, such that subdivisions of your polytope give rise to exact sequences in the image of the functor. And this would be kind of extending the fact that valuations are inclusion-exclusion invariants. And in fact, the second approach has been done. It was done at the end of last year. This is the study of categorical valuations by Elias, Miata, Brodfeld, and Petri. And they basically this. I mean, they're more sophisticated than this, but this is the idea they pursue. And they use this to prove that there's some interesting quote unquote categorical valuations. They show that the Orlik-Solomon algebra and the Chow-ring of matroids viewed as graded vector spaces satisfy this condition. Now, this is a little bit ahistorical because when I wrote this paper, this was before this paper came out. And it's not that I was trying to do the same thing, but I was thinking about this first problem over here. I was trying to see if I could categorify the space of indicator functions in a natural way. Now, there's a problem, of course, which is that it's not really clear. I mean, when you categorify something, it's always, there's lots of choices and you want to make sure you're doing something natural. And it's not very clear what one should do exactly. So instead of doing it at the space of polytopes, I want to go a little bit into the world of geometry. So in the world of toric geometry, right, here I'm going to assume smooth and projected for everything we're seeing. We have an assignment between fans, which have a lattice point in every ray, and toric varieties. And when you're nice, like we're nice here, we've seen in various talks that there are descriptions of the divisors or line bundles in terms of polytopes. In particular, if you care about the NAF T covariant line bundles, these are in bijection with a certain class of polytopes based on your fan. This polytope is a deformation cone. It's all the polytopes, lattice polytopes, whose normal fan coarses the original fan. And so this is somehow a combinatorial description of NAF line bundles. And likewise, if you don't care about the T covariance, the thing you're studying at the end of the day are the same class of polytopes up to lattice translations. So you might have seen the description in terms of divisors, where every divisor is linearly equivalent to a sum of torus invariant divisors, which amounts to giving you a number for every ray of your fan. And so then along that ray, you walk that distance and drop your half space. And so at every ray, you're building a half space, and that gives you a polytope in the center. And when you're NEF, that polytope tells you a lot about your line bundle or your divisor. Okay. So in this story, this relates to the theory of indicator functions by a result approximately Morelli. I'll say more in a second, which goes like this. So for nice fans, I'm going to assume especially a nice case, the equivariant K theory and the ordinary K theory, which are certain invariants associated with variety that describe the line bundles and vector bundles and sheaves more generally of your object, can be expressed in terms of the space of indicator functions for those classes of polytopes given by the deformation. So equivariant K-theory is the indicator functions of the polytopes which correspond to this normal fan as indicator functions. Oops. And the map is the map you would want, which is that the indicator function of a polytope gets sent to the corresponding line bundle. Okay. And likewise, there is a non-equivariant version where you take the polytopes up to lattice translations. Now, when I say approximately, this is not exactly the way Morelli stated it, but this is an equivalent form. This is described in the appendix of Chris's, Juni's, and Matt's paper. So look at that if you want to see more information on this. Probably the best source on this sort of topic. Okay. And this thing down here is closely related to McMillan's polytope algebra. This is also something that appears in the study of subdivisions and valuations, but it's normally defined a little bit differently. And when you have general classes of P, they indeed are different. And for fans, I'm pretty sure they're different, but I don't know an explicit example. Maybe Matt's nodding, so I guess he has an explicit example. Yeah, so this is not always the same as the form polytope algebra. Okay. So, and specifically for the permutahedral variety, for the permutahedral fan, the fan of the type A braid arrangement, or rather the normal fan of this, the deformation cone consists of all generalized permutahedra up to lattice translations. And generalized permutahedra are these polytopes that were first studied in the world of optimization by Edmonds, the name of polymatroids. But these are deformations of this permutahedron, beloved polytopes that appear everywhere in our community. There's a nice result that's, I think, kind of basic result in the world of optimization, which states that every generalized permutahedron can be subdivided into translates of matrix polytopes. And the statement is kind of, you just take the coordinate hyperplanes and you look at all the lattice translations, and this forms like a grid. Then you place your generalized permutahedron on that grid, and that subdivision will be into matrix polytopes. Of course, everything lives in a cube, so you can say things, but the nice thing is that this is actually a good subdivision. So this implies, before we say the K-theory part, if you look at Dirksen-Fink's result, that tells you every matroid is a linear combination of indicator functions of Schubert matrices, whatever those might be. And then every generalized permutahedron is a linear combination of matrix polytopes by inclusion and exclusion. So that tells you that you have a basis given by translations of Schuberts. And so this gives you a basis on the K-theory side. So you have the line bundles given by loopless Schubert matrix. The loopless here is just to make sure we don't double count by translations. If your polytope has a loop, you can translate it and change that loop into a co-loop. And that gives you the same line bundle, even though they're different matrices, technically speaking. So loopness is just make sure we choose one representative for every translation class. And so this gives you a basis for K-theory by the result of Dirksen and Fink. And there are generalizations of this K-theoretic statement and also the geometric statements to the stellahedron by Chris, Juni, and Matt, as well as the type B permutahedron by Chris, Alex, Matt, and Hunter. And I think are you gonna be talking about this sort of results?
Not directly.
Not directly.
Same
Yeah.
paper.
Same paper, yeah. There's a lot of that paper. Okay, so why does this help? Well, the space of indicator functions is not entirely clear how to categorify. However, K-theory from the world of the algebraic geometers has had multiple, and maybe there's like a canonical categorification. And that is where this word, derived categories, come in. So the derived category is something one can associate to an abelian category. So this is a category for where you can say the word exact sequence very nicely. And this is a category which one should think of as, in some sense, a universal cohomological invariant. Okay. It has this nice universality property definition, but I'm not going to go into the details of it. For a variety, for a nice variety, smooth projective, let's say, we can define the derived category, the bounded derived category, as the one corresponding to the category of coherent sheaves, which forms an abelian category. In terms of objects, these are complexes of sheaves. But really, what I want you to imagine is that we have these line bundles sitting inside this category. And in fact, line bundles actually generate this category when you're toric, which is nice, which means that you can think of these objects mostly as complexes of polytopes. And that is a really appealing, because when we're doing this categorification of valuations, we kind of want exact sequences of algebraic invariants. So that's already a plus. Now, the morphisms in this category are very difficult to compute. This is a hard thing to understand. Now, why do people care about the derived category just as an object on its own? Well, the main thing, well, first of all, it's a natural place to do lots of constructions like radial duality, derived functors, and so on. But one of the reasons that I think is very pretty is that passing through the derived category often reveals interesting partial equivalences, or maybe cohomological equivalence of some sort, between different categories. For instance, there is a notion of a study of modules on quivers, so let's say representations on quivers. And what I'm doing there is I'm assigning a vector space to every vertex and a morphism to every arrow. And I'm studying these sort of things up to reasonable concepts of morphisms and so on. Something that's true is that the category of representations of this quiver and the category of representations of this quiver are not the same. They're different. However, they share lots of very similar properties. And I mean, this was known way before the derived categories, but it's equivalence in terms of the derived categories. It's telling you that even though they're not the same category, once you pass to this kind of localization, this quotient type construction, they become the same. The most interesting examples of this are when you have objects from completely different fields. The most famous one you probably heard about is homological mirror symmetry, which takes you from some algebraic geometric concept, the derived category of the variety, to some symplectic geometric construction, the Foucault category. But another one of that form is this result by Bellinson, where he shows that the derived category of CP1 can be described as very beautifully as a derived category of representations of the so-called chronic equivalent. And of course, he describes derived categories of higher CP. But this is very striking result.
What did you call this quiver?
The chronic quiver is the name people use for it. Okay, so this is nice, right? It has complexes in it. It's kind of looking like a good categorification. However, someone would and should complain. I just went over to K-theory and then I categorified K-theory, right? Somehow I lost all the convex geometric information. Now, the thing that started this paper is that I found the following result. There's a beautiful paper titled The Categorification of Morelli's theorem. The Morelli's theorem is this result that related the space of indicator functions to the K-theory. And it turns out that result can be categorified. And this fits into a sort of general framework that's called the coherent constructible correspondence. And it tells you that the derived category of coherent sheaves can be understood as sort of sheaves on Rn. This is the original version by von Daum. And the equivariant version in a weakened form is the following. You take T covariant coherent sheaves and you land on the derived category of sheaves on Rn. Now, I know this is, it looks less, more opaque than maybe even the derived category. But the nice thing about this construction is that we can trace where certain line bundles go. If you take the dual of an ample line bundle, an anti-ample line bundle, the thing it maps to is a push forward of a constant sheaf on the polytope. So what you do is you take the interior polytope, you view the constant sheaf on that, and then you push it forward into Rn in a derived sense. Now, of course, there's homological algebra here, but I want you to, for a second to imagine what these sheaves look like if we didn't have any of these DG push forwards. This is a polytope, and I have this sheaf on the polytope. When I look at the stalks outside of the polytope will be 0, and the stalks in the polytope will be C. And so this is kind of taking the role of the indicator function. And in fact, if you take K-theory of both sides, that map I just described, you take the stalks, is actually the map that's sending it to indicator functions. So actually, this also reproves the statement that Morelli's theorem can be phrased in terms of polytopes. But
Is there any condition on sigma?
yes, so sigma, well, their full statement works for sigma projective. You don't even need smooth. Yeah. Although you have to be careful about what this category is. You have to replace it by category of perfect complexes. But there's versions for projective non-string. Yeah.
Is that little circ P mean interior of the?
Interior of the polytope, yeah. Otherwise, you wouldn't have yeah, so you take the interior of the polytope and you take the constant sheaf. So really, you're studying constant sheaves on polytopes, these sort of polyhedral sheaves. Yeah.
Is the theorem just that there's an embedding like this, or is there some description of the central image of function?
Yeah, Bondell's theorem is exactly this. And the FLTC theorem is, first of all, stronger. It's in the DG context, and they completely tell you what the image is. You land in compactly supported constructible sheaves with respect to certain Winnie certification coming from this, and it has particular singular support, which is kind of telling you what the cones look like at the vertices of this sheaf. So they completely describe the image.
You say where LP goes in an easy way?
Yeah, I mean, there is a description in terms of like sheiks and stuff like that, but.
Okay.
Yeah, so this thing appears in the literature, it's called the co-standard constructible sheaf. And the other one goes to the standard constructible sheaf, which you can look up in David Nadler and Eric Sass as well. Okay. Okay. So this is where I'm going to take a leap, and this is kind of just a hunch. But for me already, there's been a lot of interesting similarities between this category and the category of space of indicator functions. And in particular, it has some things that are nice, like I have exact sequences of polytopes in this category. And so this is the thing I want to think about. And so as a sanity check, the thing I wanted was to know that Dirksen and Fink's basis extended to this category, and whatever that means. And so the first question is, what does it mean for, what is a reasonable notion of basis for these categories? And there's lots of different things that could take that role, but there's a very specific, very strong notion of generation for a category called having a full, strongly exceptional collection, in particular of line bundles. And so what this means is that you have a collection of line bundles that satisfy two technical algebraic geometric conditions. The first is that they generate the category as a triangulated category, as a thick triangulated category, whatever that means. And the second is that there's no higher extensions between the line bundles. These are algebraic geometric conditions. And this was originally conjectured to be true, that every smooth projective fan, maybe smooth complete as well, but at least smooth projective fan has such a collection. But this ended up being quite false. A lot of people, including our fellow wizard here, also has a nice example. Yeah, so this turns out to be quite false. And in particular, it's even false for the Fano case. So it's really not really redeemable. However, there are certain examples where there are such collections. And the upshot is I'm going to end up showing, or the thing I show is that if this is a permutahedral variety, then it satisfies this condition. So one of the nice consequences of having such a collection is that if you have such a collection, then that implies that your derived category can be described as a derived category of modules over some quiver with relations. And by this, I mean you take the path algebra and you push it by some ideal. And that quiver can be explicitly read off the line bundles. And so this phenomenon of Bellinson that CP1 was the Kronecker quiver, the modules of Kronecker quiver, extends whenever you have such a collection. And so this gives you a kind of fairly explicit description of the category in terms of modules. So there's all this algebraic geometry, right? And all this higher extensions and generation triangular categories and so on. The goal I set out with was to, well, try to find a convex geometric way of approaching these problems, or at least somewhat convex geometric way. The basic idea is that we have this constructible correspondence, which replaces my line bundles by things that look like polytopes. And so I know how to deal with polytopes. And so the hope was that the knowledge of polytopes downstairs in the space of indicator functions can somehow extend and give us proofs of statements upstairs. And I'm not going to talk about the actual translation. There's a lot of results that go into this. It's not that hard once you know the relevant background, but I want to show you what the end result is. So what I want to talk about now, and for the remainder of the time, is not more derived categories, but rather I want to give you some conditions on polytopes that will imply these conditions at the derived category level. Okay. Any questions at this point?
What is the derived category you're thinking of right now?
So this is the derived category. So the thing I'm thinking about in general is the derived category of bounded complexes for toric varieties, smooth projective. But at the end of the day, we're going to care about the permutahedron and some related varieties.
Thanks.
Okay, so most things in toric geometry have convex descriptions. And so the goal or the hope is that there's also a convex description of derived categories. And so what I'm going to talk about are some conditions on polytopes. I'm going to tell you what it means for polytopes to be strongly exceptional here, and what it means for them to be full. And the point is that these are implying the related results in the world of line bundles. So I say that collection of polytopes are strongly exceptional if the following condition is true. If you take the set difference of one polytope and the translation of another for any lattice translation, then that set difference is either contractible or empty. This is contractible in the sense of topology, You can squish it up into a point without making any new holes. So this thing has no holes. Now, in general, if you take set difference of polytopes, you can do very bad things. You can imagine a cube and you take away like a triangle in the middle, and you create a bunch of loops somewhere in the middle. So things can be very nasty. And so let's think about an example. So if we think about the toric variety associated to this polytope, and by this I mean the fan of this polytope, then this is the toric variety CP2. And for that variety, we can immediately see from the polytopic perspective that these polytopes are strongly exceptional. Okay. You can take, for instance, this triangle here and do any lattice translation over here, lattice translation. And no matter how you do the lattice translation, that will be contractible. Likewise, if we take this point, you can only take away points on the boundary, which will still be contractible. However, note that we can't add this, this triangle. If you try to, this point in the center, you'll be able to move it in the center and make a punctured disk. And this is telling you that, so this is O01, O2, O3, this is telling you there's extensions there. Algebraic geometric point of view.
Is this contractible equivalent to it not having any reduced cohomology?
I wish I knew that sort of statement, but that sort of thing sounds really scary. Yeah. So in general, being contractible is really, I want acyclic, but I'm just gonna, for expositor. Okay, and the second thing is this fullness condition, and I went back and forth whether to actually talk about the full definition of it, and I ultimately decided against it just because it takes a lot of time to explain. So instead, I'm going to give you a weaker version that will work for the examples I'll show you. And so I'll use this word weak subdivision, which I probably shouldn't use, to refer to the following concept. So a weak subdivision of a polytope inside my deformation cone is going to be a finite collection of polytopes with the property that their union is the entire polytope, and their intersection is in my deformation cone or it's empty, I guess I should say. So it's either my deformation cone or it's empty. As an example, let's think about CP2 again. Here's a polytope. I'm going to give you a weak subdivision of it within this fan. So first what I'm going to do is I'm going to take this second dilation of my triangle and put it at the corner. I'm going to get another second dilation and translate it over by 1. Note that these two things intersect at a smaller triangle, which is still within my deformation cone. And finally, I'm going to take 1 and shift it up to the top. Now, the intersection of any two triangles is a smaller triangle, and the intersection of all 3 is a point, which is in my fan. So this is a weak subdivision of that third dilation of the triangle. And this is giving an exact sequences of O3 in terms of the other O's. So I'm going to say that a collection is full if it satisfies the following property. Every polytope in my deformation cone can be weakly subdivided by translations of polytopes in P. And this is a really weak statement, but it's nice for postulated purposes. Okay. So for example, this collection of polytopes is full. The example I gave you before showed you what the third dilation of the triangle looks like. And it's not that hard to copy that argument for the general translations. And you can also think about what this looks like for higher simplices. And it will be true that you can find a nice generating set for the higher simplices. And that's something you should try. Okay. So these definitions are set up so that a smooth projective variety, for a smooth projective variety, if your collection of polytopes satisfies both this full condition and the strong exceptionality condition, then the collection of polytopes you have at the end are going to be full, strong, and exceptional as well. This is not a converse because I'm showing you a really weak version. And even in the strongest version, it's not a converse, I think. At least I didn't show it was. Okay. So I want to work out another example.
These are known examples of toric varieties with full strongly exceptional collection.
Without one?
Yeah.
Because I think the example you have.
Violate this condition in terms of polytope, the stronger condition.
Very strong condition. Yes. Sorry, what did you mean? Violates a stronger condition?
And if I look at those examples, I won't be able to find the polytopes that satisfies the weak subdivision property.
Yeah, so the problem that happens, so I think you have like Pn blown up at 2 points or something. It's like a very simple example. And what happens there is that there isn't a big enough collection of polytopes which are all exceptional. So something that you know is true is that if you have an exceptional collection like this, then it will necessarily form a basis for the K-ring. And so what that means is that you actually know how many you're supposed to have. You're supposed to have as many as the number of vertices. And so to construct counterexamples, what people do is just compute a bunch of line bundles and show that you cannot have a exceptional collection of big enough size. So incidentally, if you find enough polytopes and you prove this condition, this implies that it's a basis for the K-ring, which can be used to give sort of new proofs for a lot of K-theory results. But okay, let me talk about an example. So let's talk about this example. This is the example of the trapezoid. This is the Hershey surface, H1. And so here's the fan of this polytope. And first thing we're going to do is we're going to just talk about the coarsenings of this fan. Right? So here we have 3 coarsenings. What we can do is we can coarsen everything, which will give us this, and the polytopes look like points in that case. We can coarsen the 2 left cones and the 2 right cones, and that will give us things that look like line segments and dilations of line segments. And finally, we can coarsen in this way the top 2 cones, and this will give us triangles and the dilations of these simplices of these triangles. And these are in some sense all the different types of the polytopes you can get. In fact, these generate the NEF cone. That's neither here nor there. So here's a calculation of the derived category for H1. So I claim that these 4 polytopes form a full Schrodinger exception collection. So the first thing we can do is we can talk about exceptionality. And this can be done by just kind of looking at them in this 2-dimensional case. I mean, you can just try out all possible translations. You'll see that there's no way to translate this to create any bad, to make it not contractible. The more interesting thing is showing that it's full. And so in this case, actually, weak subdivision also helps. And so I'm going to show that any polytope in this thing can be weakly subdivided by these 4 polytopes. And this is a generic polytope in this fan. And so let me show you how to do it for this. So the first thing I'm going to do is just view this strip by strip. And this already weakly subdivides my polytope into these polytopes, which are still in the deformation cone, as well as the intersections, which are giant lines, which are my intersection cone. Now I'm going to subdivide each individual strip. And I'm only going to do it for the bottom one. And I'm going to follow the same idea I tried for the simplex. I'm just going to take the trapezoid in the bottom left. And then I'm going to consider another trapezoid and move it over. And the magic of this situation is that the intersection is a triangle, which is a triangle up here. And so I can repeat this all the way across. This gives me a subdivision that looks something like this. Okay. So doing this gives you can repeat this on every strip, and this gives you a pretty much a picture proof of the calculation of the derived category of H1.
For this weak subdivisions, do you care that the intersection is in a deformation cone or it's from your list?
So a weak subdivision in general means that you want it to be in deformation cone. For a family to be full, you want every polytope to have a weak subdivision where the, I guess, minimal pieces or all the pieces that appear in the subdivision are from your family. So in this case, every piece is from my family, which means that it's a full collection.
That would mean that you can do indicator function by linear combinations of things from your family.
Yes, yes. So this is a categorical statement. At the K-theory statement, this is an indicator function statement. But the point is that this sort of arguments extend. And so the theorem then, which I don't know if I definitely won't have time to talk about, is that one can use this method to construct full Schrodinger exception collections for 3 varieties. The first, the Permutahedral variety, which is also known in some communities as the Lewis-Madden space, has a full Schrodinger exception collection given by the base polytopes of looplet Schubert matrix, which is actually exactly what we wanted. This is the categorification of Dirksen and Fink's result. So this category, which is supposed to be playing the role of the space of indicator functions, indeed has a basis in a very strong sense that mimics the Dirksen-Fink result. And then I did it for other varieties following the lead of some people in the audience. So for the Categorifying variety, there's a K-theory result, as I mentioned, by Johan Larsen, where they show that these independence polytopes of Schubert matrix give you a basis for the K. And indeed, that result categorifies, that gives you a basis for this derived category. And finally, we have the same thing for the type B results by, this is Chris, Matt, Alex, and Hunter Spink. And so these are categorifying these results. Now, this variety here is also, by the way, a modular space. I mean, so is this, I guess. But this is has a compactification. I forget how many heavy points. I think 2 heavy points. Heavy points, yeah. And the type B also has some interpretation in terms of sort of chains of lines with respect to some nice involution. Okay, so I mentioned that having a full Schrodinger central collection gives rise to a quiver description of the category. And so for all of these categories, I have a quiver description where the vertices are indexed by these corresponding matrices. And the nice thing about this, which is not, the nice thing about this is that these quivers can be described purely in terms of matrix theory. So these are quivers of relations. In particular, these are labeled quivers. And I'm insisting that when you take two paths where the labels give you the same sets at the end, I'm insisting those two paths give you the same element in the path object. So that's the ideal that I'm describing. And so here is the quiver with respect to those 5 polytopes. The matrix theory description is actually fairly nice. There's an arrow whenever without label, whenever one matroid is there's a weak map from one matrix to another. So the unlabeled arrows correspond to weak maps of matrices. And the labeled arrows are very close to weak maps, except you're allowed to turn a code loop to a loop. And this records which code loop you change to a. Okay, so purely matrix theoretical. There are similar descriptions for the Permutahedron and type B. Okay, there are some related results and about this variety in this collection. So the previous results that was known for this Los-Amanin space of the Permutahedral variety was the result of Kashavet and Tevelev. They were studying trying to find nice full exceptional collections of the varieties. So their motivation comes from trying to study the derived category of M0 and bar, where there are some nice symmetries. And the goal is to find a collection which is invariant under the symmetries of your variety. So in this case, the symmetries of the marked points for M0 and bar. And the traditional methods that people use to describe derived categories didn't quite work because they broke the symmetry in a certain sense. And so they came up with a different method that allows them to compute it for the Permutahedral variety. However, their statement, right? And so my statement straightens their statement. It's a stronger result. And it's stronger in 2 ways. First of all, they don't have the word strong. So mine is a strong exceptional collection, which is a stronger notion of generation. And also instead of sheaves, you can actually take line bundles. So this result is actually immediate from the description. So saying that the collection of polytopes are invariant under these actions, saying that the line bundles are invariant under these actions is the same thing as saying that the polytopes are invariant under the corresponding actions. So the SN action here permutes my polytopes, but I'm considering Schubert matrix up to isomorphism, so it's already up to isomorphism. The more interesting one is the additional symmetry of the braid fan, which in the Permutahedral writing, this is a map called the Cremona transform, Cremona symmetry. In that case, that corresponds to multiplying your polytope by -1. And it turns out if you multiply your polytope, your matrix polytope by -1, and then you allow translations, this is actually just giving you matrix duality. And then the corresponding statement here is that Schubert matrices are closed under duality. And so those 2 statements imply this symmetry result. And there are similar symmetry results for the Categorifying variety and the Permutahedral variety. So there's 2 things to say. First of all, from the perspective of the derived category people, they care about finding these nice collections. And this is a combinatorial method that gives you those collections by essentially drawing pictures. Of course, as soon as you get to higher dimensions, it becomes very tricky to say when the set difference of 2 polytopes is contractible. It's a very difficult thing to do. But the second thing is that this result really sort of tells me deep inside my soul that this is somehow the right analog of the space of indicative functions. It has a similar result that's like there's an think, and it has exact sequences. And in fact, if you study this derived category, you can prove results in the categorical valuations, this other approach to this categorification. This is related in a very direct way. So what's next? Now, this toric geometric method is not just for these varieties that works for general smooth projective fans. So in particular, the thing I'm very interested in is trying to understand the Lode realization of the associated. This is a generalized multihedron, and there's a couple of different realizations corresponding to linear orders. And so what I want to know, a very first question, is I don't even know that many families of polytopes of the correct size. So the results, the general theory tells you that you're looking for as many polytopes as vertices. And so the first question is, do you know how many polytopes which deform the associahedron? Okay. The next thing will be to check, of course, that these are exceptional. Now, I've asked various people around, and I've gotten basically two families of examples. One coming from anti-chains of the root post set, and the other coming from cluster algebras, where you associate a polytope to every cluster seed in the type A quiver. And these are beautiful polytopes. Unfortunately, they fail the exceptionality condition. So those two classes of polytopes do not work. For the two-dimensional case, I have these 5 polytopes here, and you can check if these work. But I don't know how to do this in general. So if you know any kind of these polytopes, please come let me know. And yeah, that's all I have to say. So.
Is there something you could say about the equivariant category for permutahedral set?
Yeah, so there's results. I guess the person to look up, Elegant, I think that's how you spell his name, has many results that if you have a nice collection on a variety. So I thought about what it looks like for the SN, right? The SN stack. And he has some results about what this means for the derived category of the SN stack. The problem, if I remember correctly, is that it breaks the line bundle condition. And so the things you get are no longer line bundles. And also, I think it also breaks strong exception.
I meant torus equivariant.
Oh, torus equivariant. Sorry, I thought you meant a different group.
Yeah.
So for torus equivariant, I mean, I haven't thought about it, but yes.
But is there like a statement, like, because I mean, I guess fully strong set doesn't quite make sense. If it's a finite collection.
It doesn't make sense.
Well, it's just like, I mean, the K group is like huge now, right? It's infinite rank.
Yeah, so I would have an infinite. I think it's just like you take all translations of Schubert matrix. Yes, I'm pretty sure that works. Yeah.
Okay.
So it's kind of a silly statement, but yeah. So you take all translations of Schubert matrix. They're still exceptional. There's a T-covariant formula for calculating exceptionality. You get rid of the translation, and all the fullness arguments still work.
And you can still order them in such a way, reasonable way. You don't have to put like infinite limiting points first, then.
That's a good question. I don't know. Let me think about that.
Following up on our math overflow discussion yesterday, what's special about like types A and B here?
Right. So
Or what's June would prefer to say, what's interesting about
yeah, okay. So first of all, there's two problems in type C. The first problem is maybe a problem that maybe you'll talk about, but it appears in Matt's paper with Chris and Alex Hunter, which is that this argument that you like take your coordinate hyperplanes and you translate them from a grid and you put your polytope on it and you let that subdivide into matroids, that argument fails in type C. So there is no way to at least no way that I know to subdivide a type C genotahedron into major polytopes. That's the first problem. The second problem is that if you take the definition that like Petriev and Bloom have of these toric varieties of type C, then you can just say, okay, well, let me just take the same family of Schubert matrix anyways. I'm gonna take the type of Schubert matrix and I'm gonna just try to see if they satisfy exceptionality. And that fails because the square, even in two dimensions, the square has an interior lattice point. So as soon as you go to type C, the lattice changes, you get new translations that are allowed, and those translations break this contractibility condition. Now, why? I have no clue. I did try sitting down with the two-dimensional type C permutahedral variety and just trying to find a different exceptional collection. I couldn't.
Type D is the same problem, right?
Yeah, well, I haven't checked, but I assume so, yeah. So I can't find one for even the two-dimensional one, just.
Yeah, I don't know, this is like comment, so do you actually like, because you wrote down association, do you like expect there's some possible conceptual issue when you try to do this with other generalized permutahedron? Or is it just like you haven't tried it?
Sorry, what was the question for, for other general data?
Yeah, I mean, I guess my question is just like, is it just because you haven't tried, or do you anticipate there's some conceptual problem?
Yeah, so, I mean, the associative variety I care for a couple of reasons. One is that it's a wonderful variety. And the second is that we have a very good description of all possible deformations. So you need to know all possible deformations in a nice way so that you can have any hope to describe things. And so we know, I forget exactly who the various authors are, but Vincent Bellot has a series of papers.
The operator.
What's that?
You mean related to operahedron zone, or? Do you mean related to operahedron zone, or?
So this is nestahedra.
Oh, okay.
Yeah, so he has a paper where he describes the Neff cones of possible deformations for various different types of nestahedra. And so there are other things for which we know the Neff cone, like the very cool one is that there's like this Tesla polytope construction. And I forget exactly what the situation is, but there's a general Tesla polytope. And the Neff cone of that general one, the generic one, is all other Tesla polytopes. And so the Neff cone is very, very concrete. And so you can sit down and try to plug it into a computer and see if you can find a family that will give you the set differentiation. But that's why I care about this one.
Right.
One, it's doable, and two, well, it's a wonderful variety, which is pretty.
Thanks.
Any other question?
So sorry, your condition on exceptionality when you like take the difference and shift, this one was even on leaf and only fullness was not even on leaf, or that one is not?
If you replace contractible by acyclic, then yes. And Matt's question is, are these the same? Which I think I asked someone and they got scared. It's a scary question if those are things like that.
Could you check this associated question for three-dimensional with the computer by kind of like exhaustive search?
Yes, and embarrassingly I haven't. So, yeah, but we know the Neff cone, so you can just look all the small polytopes and just check. And I'm pretty sure you can make an argument, like if all the small enough polytopes don't work, you can probably break everything. So this is something that should definitely be done. If anyone has, I actually have code that computes whether or not the set difference is contractible. So I'll chat later.
Other questions? Yes.
Yeah, this is not another just minor comment, so, do you have any idea what sort of subdivisions can just go in the other direction can occur as like something occurring for an SAC?
What sort of subdivision?
You said you want some kind of nice subdivision, do you know like what kinds of subdivisions can actually like be realized using this?
Yeah, I'm not entirely sure. In this case, what you can do, so the way you arrive at this family is, let me see if I can do it on the spot. I think you take this hyperplane, that hyperplane, and you translate those around. And so we're doing the same trick, trying to come up with a nice collection of polytopes so that when you subdivide it by this grid, you get small polytopes, and then it becomes like a finite check, right? And so this is part of the hope that this will work. This is what you were asking?
It's okay, maybe we can talk.
Yeah, we can talk later, yeah.
Maybe a bit naive, but do you have any hope for something like a Fourier Mukai between like, I don't know, an X sigma and sigma polar?
Yeah, so one of the things I do have a hope for, this is not about the permutahedron, but about the associahedron, is that there's actually lots of different realizations of the associahedron, even within like as a generalized permutahedron. And these realizations give you different toric varieties. However, their K theory, their Neff cones all look very similar. And so the hope would be to give some explicit description of these objects. And this is not necessarily Fourier Mukai type stuff, but in the case of associative fan, something close to algebra people do is they go from one fan to another by doing like blow ups and blow downs. And so they have some sort of stellahedral subdivision argument that gets you from one fan to another. And so one could definitely try to use that to do some sort of flip-flop argument showing that things are the same. And so there's definitely questions there. I don't know enough about the machinery to be able to do it myself.
Any other questions? Okay, now let's thank Mario again.